Welcome back to Module 2 of the training course on the fundamentals of FWD and back calculation of the principles and application of the BCT, which is the back calculation tool for rehabilitation design using the PMed software course. Referring back to the BCT training course roadmap, you just finished Session 2 in Module 2. This portion is Session 3 of Module 2 and discusses the back calculation procedure and process. There are 5 learning outcomes from Session 3 of Module 2. These include being able to describe the different methods to calculate elastic layer moduli from deflection basins, list programs available for back calculation of elastic layer moduli, state the assumptions and limitations of back calculation, list the inputs needed for back calculation, and finally, explain the differences between back-calculated and laboratory-derived elastic or resilient modulus. 6 topics will be covered in this session. The first is an overview of back calculation. The second is programs for back calculation. The third is the different assumption in back calculation. The fourth includes EverCalc that is used in the BCT. The fifth is the process and procedure of back calculation. And the sixth is the outcome from the BCT, which is back-calculated elastic layer modulus versus the laboratory-derived resilient or elastic modulus. Back calculation of elastic layer moduli is the most common method of analysis of deflection data when used for rehabilitation design. First, let's start with the definition of back calculation. Back calculation is to estimate the elastic modulus of each structural layer in the pavement and foundation from deflection basins. The back-calculated elastic layer moduli are derived or determined by minimizing the difference between the measured and calculated deflection basins. Deflection basins and back-calculated elastic layer moduli are used for 3 major areas. First is pavement evaluation. Second is rehabilitation and overlay design, which is the focus of this training course in support of the PMed software. And finally, forensic investigations. Estimating the elastic layer moduli from deflection basins can be grouped into 2 major methods. One is defined as the forward calculation method, and the second is defined as the back calculation method. Both methods use deflection basin data but rely on different approaches which will result in different elastic layer modulus values. The forward calculation method uses deflections measured at specific sensors located from the loading plate, and the results are unique. In other words, a single set of elastic layer moduli will be calculated based on the pavement layer thicknesses simulation. The back calculation method uses deflections measured for all sensors in the deflection basin and is based on an iterative procedure in matching the measured and calculated deflection basins. The best set of elastic layer moduli is based on minimizing the differences between the measured and calculated deflection basins. Unlike the forward calculation method, the back calculation method can result in multiple sets of layer moduli for the simulated pavement structure. Over the years, researchers and practitioners have developed numerous approaches to back calculate pavement layer and subgrade moduli, as well as numerous software programs to perform the calculations. Some publicly available programs are BAC-FAA, developed by the Federal Aviation Administration, ChevDef, developed by the Waterways Experiment Station, or WES, of the United States Army Corps of Engineers, EverCalc program, developed by the Research Initiatives by Washington DOT, MISHBAC, developed by the Michigan State, ModTag, developed and used by Virginia Department of Transportation, Modulus 6, that was developed by Texas Transportation Institute, PCASE 2.08, also developed by the United States Army Corps of Engineers, and WESTEF, developed by Waterways Experiment Station, or WES, of the Army Corps of Engineers as well. Some back calculation programs that are not open source include BizDef and ComDef, developed by the Waterways Experiment Station of the United States Army Corps of Engineers, so they've developed a number of back calculation programs. DB Compass is a research product by the University of Florida and is exclusively for rigid pavements. LMOD is a proprietary back calculation tool developed by Dynatest. Illibac was developed by a University of Illinois professor and is also for rigid pavements. And finally, PAYDAL was developed by researchers at Nottingham. All of these programs have their own advantages and limitations, and for any pavement system, the engineer should be very well versed in the tool's proper use and limitations. Now let's look into EverCalc, the engine of BCT. EverCalc is a mechanistic-based pavement analysis computer program that is embedded inside the BCT to estimate the elastic moduli of pavement layers from deflection basin data. It uses the backcalculation method or approach. The program has been primarily used for the analysis of flexible pavement using FWD deflection measurements, but is applicable to rigid pavement in estimating the elastic modulus of the PCC slab using deflection data measured near the mid-slab or interior of the slab. It can also determine the stress sensitivity coefficients, which are K values for the base materials and subgrade soil when the FWD data for at least 2 load levels are available at a given point. Furthermore, the asphalt layer moduli can be adjusted to standard laboratory conditions or a standard load and temperature. It can compute stresses and strains at various depths of the pavement. There are some specific assumptions based on which EverCalc has been built. The assumptions are based on quasi-static, layered elastic theory. Layers are indefinitely long in the horizontal directions. In other words, anisotropic conditions and cracks or defects cannot be directly simulated. Anisotropic conditions means the properties in the vertical direction can be different from the horizontal direction. Layers have uniform thicknesses within a design segment. The layers are composed of homogeneous isotropic linearly elastic materials characterized by elastic modulus and Poisson's ratio. Isotropic means the properties in the vertical direction are the same as in the horizontal direction. No discontinuities, such as crack and/or joints, simulated in the pavement structure. And finally, static load applied from the NDT device. Another assumption or limitation of EverCalc and some other back calculation programs in the public domain is the pavement structure and subgrade is limited to a maximum of 5 layers. The maximum number of layers restriction will be discussed in more detail later in this training course. As we noted earlier in this training course, EverCalc uses an iterative approach to estimate a set of elastic layer moduli in a layered elastic solution, so the calculated and measured deflection basins are within some tolerance. If the user changes the tolerance, different elastic moduli will be estimated for the simulated pavement structure. The inputs to EverCalc are grouped into the load and layer inputs and the FWD measured deflection inputs. The FWD measured deflections include the FWD loads from one or multiple drop heights, the diameter of the loading plate, the number of sensors, the spacing of the sensors, and obviously the deflections measured at each sensor. The load and layer inputs included for each layer in structure simulation: the layer thickness, Poisson's ratio, upper and lower elastic layer moduli, and the starting or seed modulus used to start the beginning of the iteration process. The back calculation process used by EverCalc will be overviewed on this slide. The EverCalc program uses Wesleya, provided by the Waterways Experiment Station, U.S. Army Corps of Engineers, as the layered elastic solution to compute the theoretical deflection and a modified augmented Gauss-Newton algorithm for optimization. Next, the computed theoretical deflections are compared with the measured FWD deflections. A default tolerance is used internally within EverCalc to determine if the deflection difference between the measured and calculated deflection basins are within the tolerance. In the standalone EverCalc program, the tolerance can be revised or changed. However, for the EverCalc program included in the BCT, the tolerance is set to a standard or default value. If the differences are greater than the tolerable limit, the elastic layer modulus is revised, and the deflection basin is recalculated and compared to the measured deflection and tolerance. When the difference between the measured and computed deflection is within the tolerance, the final set of elastic layer moduli are reported from the program. EverCalc calculates the root mean squared error between the calculated and the measured deflection basins for each test point and drop height. The user decides to set a root mean squared value to eliminate the set of elastic layer moduli that are greater than the specific root mean squared error. Some more details about EverCalc. The back calculation procedure using EverCalc is an inverse solution technique that is used to determine elastic moduli from FWD pavement surface deflection measurements. This program can handle up to 10 sensors and 12 drops per station. The program is capable of evaluating a flexible pavement structure containing up to 5 layers. The deflections calculated using Westlia algorithm is compared with the measured ones at each iteration. When the root mean square RMS error between calculated and measured deflections or changes in the modulus falls within the allowable tolerance, or the number of iteration has reached a maximum limit, the program terminates. The outcomes from the back calculation process are: a representative set of layer moduli exists for a particular loading condition and temperature condition, such that the theoretical or calculated deflection basin should closely approximate the measured deflection basin. Although, in reality, depending on the tolerance allowed in the procedure and the relative number of layers compared to the number of deflection sensors, several combinations of moduli may cause the two basins to match reasonably well. The more the user knows about the pavement and its simulation, the better the results. Two important requirements by the user are knowledge of the layer condition and structure, and a close approximation of the layer thickness. Engineering judgment and expertise is required accordingly, because back calculation is both a science and an art. Remember, there is no unique solution or a set of elastic layer moduli for the back calculation method or iteration process. The iteration process minimizes the tolerance between the changes in the deflection basin and elastic layer moduli, as well as reviewing the root mean squared error. This slide shows the layer thickness for a structure. If we assume that all layers are intact, and using the layer simulation rules of thumb that were included in Session 2 of Module 2, 5 layers might be simulated for this structure. High plasticity clay as layer 1, sandy clay with gravel as layer 2, lime-treated soil as layer 3, crushed limestone layer as layer 4, and combining all the asphalt or bituminous layer as layer 5. Remember from Session 2, the 8-inch lime-treated soil should be a fixed layer because it will likely be defined as a thin layer, so elastic layer modulus is fixed in the back calculation process. However, what if the lower asphalt layer exhibits stripping or disintegrates during the coring operations to determine layer thickness, as displayed on this slide? The layer simulation will be different because the load responses of the intact versus deteriorated asphalt layers will be different. This slide shows one possible option to simulate the pavement structure in back calculating the elastic layer moduli. Another option is to consider or combine the crushed limestone and lime-treated soil layers, especially if the lime-treated soil layer has sufficient lime to increase its strength and stiffness. In conclusion, the structure simulation is determined by the user based on the outcome or lower root mean squared error between the different simulations. There are several key factors that affect the back-calculated elastic layer moduli value. The back-calculated moduli is denoted here as field-derived moduli as it is getting computed from deflection testing. First, input parameters such as deflection basin parameters, layer thickness, load distribution, number of pavement layers, depth to stiff layer, seed moduli. Next, FWD testing parameters like drop height, drop weight, number of sensors, sensor location and spacing, loading plate size. Then seasonal variations such as moisture content, depth to water table, temperature profiles, frost depth. The back-calculated elastic layer modulus values are representative of the conditions at the time of deflection testing. After that, pavement condition like cracking for asphalt pavements and joint condition for concrete pavements can also affect the field modulus. Neither cracks, joints, and other defects can be directly simulated in the EverCalc, and as such the BCT back calculation program. Finally, thin layers are difficult to analyze in the BCT and other back calculation programs that are based on elastic layer theory. Remember, thin layer was defined in a previous Module 3, Session 2 under the rules of layer simulation. This ends Module 2, Session 3. The next module of the training course is Module 3, which is the BCT and PMed rehabilitation design concepts. Thank you.